Okay, welcome to lecture 2 or part 2 of our lecture series from Monday, March 6th, where we discuss some exceptions to the octet rule, one of which that we've already seen is the duet rule. So I'm going to just start by making an overarching statement here, which is that not every compound will bond such that octet is met. So for example, if I were to look at something like hydrogen gas, well, if I were to do my Lewis dot structures here, I would have hydrogen, which is 1s1, with another hydrogen, 1s1, meaning I have two valence electrons, drawing them symmetrically around one another and then connecting with a single bond. That uses up my two valence electrons. And since I have no extra electrons available to use to bond, I am totally full. Like I cannot add any more electrons around each of these hydrogens. And these hydrogens wouldn't want that anyway, because notice these are the s orbitals, and s orbitals can each contain maximum a number of 2 electrons. So once I've got this bonding pair here, which is 2 electrons, then I have already stabilized each of these hydrogen atoms by giving them a full valence shell, where that valence orbital is the s, or the 1s orbital. So this is what we call the duet rule, which we have seen already. But there are some other instances where octet is quote unquote disobeyed. The rule is not followed. So the first one is when we look at covalent compounds with atoms that possess fewer than 8 total electrons. So for example, if I wanted to do something like BCl3, first I would have to count up my valence electrons. So let's get a periodic table up here on the board, so we can count our group. So boron, this has 3 valence electrons. Chlorine, these have 7 valence electrons each, and there are 3 of them in our molecule. So that is 7 times 3 is 21, plus 3 is 24 electrons. And if I were to do my placement of my boron and my chlorines, and then connect them all with a single bond, using up 2, 4, 6 of my valence electrons, leaving 18 behind. I would then now fill in the octet of my outermost atoms using the convention where we start with the most electronegative. These are all chlorine atoms, so I'm just going to pick one. So 1, 2, 3, 4, 5, 6 of my 18 has been used. 7, 8, 9, 10, 11, 12 of my 18 has been used. 13, 14, 15, 16, 17, 18 of my electrons have been used, meaning I am out. I no longer have any electrons that I could use to start adding in electrons here on the boron. Because if you were to look at this boron, you would see, well, wait a minute. If I were counting my octets here, yes, of course, all my chlorines have met octet, 2, 4, 6, 8, because we just intentionally filled their octets. But boron is left with 2, 4, 6 valence electrons on the boron. And ultimately, in this case, that is okay, because boron itself is an element that possesses fewer than 8 total electrons. right? If I were to think about my electron configuration, 1s2, 2s2, so that's 4, 5 valence electrons. Sorry, 5 total electrons. This is going to have to be the Lewis dot structure I settled for. I don't have any further electrons. If I were to do something like create a double bond from one of my lone pairs on chlorine, you would see that your formal charges don't work out. You try that for yourself. Might be a good practice, again, if you're struggling with formal charge. But this would be an example of an exception to the octet rule. The next exception to the octet rule is for compounds that contain atoms with an odd number of total electrons. So a good example for this is nitrogen monoxide, NO. So nitrogen has, let's see here, counting our groups, 1, 2, 3, 4, 5 valence electrons. And if we were to count up, that'd be 1s2, 2s2, so that's 4, 5, 6, 7 total electrons. So that is the guy that has odd total number of electrons. And then we have a single oxygen. This has 6 valence electrons. If I were to add these together, I get my electron budget of 11 electrons. And if I were to build my Lewis dot structure according to my convention that we've been practicing, I would have nitrogen and then oxygen connect with a single bond first. That would use up 2 of my electrons, giving me 9 electrons left. Now I spend some of that electron budget to fulfill the octet of the more electronegative atom. So if we're going to compare oxygen against nitrogen, oxygen is further to the right here in this second row. So this is more electronegative. So I would fill my octet 2, 4, 6, 8. So I have, in doing so, used up 2, 4, 6 of my electrons, giving me 3 left. And if I had to place them around my nitrogen atom, which I do, right? I have to do something with them. I can't just not use them. I would see that I have 3 lone electrons on my nitrogen atom. So what would the Lewis dot structure of this be? So we would see probably something like this. So like, first of all, let's check that this, even though it's valid, is this stable. So let's do a formal charge calculation on the nitrogen and a formal charge calculation on the oxygen. So nitrogen contains 5 valence electrons when not bonded to any other species. We're going to subtract from that the sum of the number of bonding pairs attached to nitrogen, or number of lines. That is 1 bonding pair, plus the number of non-bonding electrons or dots put on the nitrogen, which is 3. This gives us a +1 charge, formal charge on the nitrogen. Let's do this for oxygen. Oxygen has 6 valence electrons when it's not bonded to anything. Here, oxygen contains just 1 bonding pair, and yet it also contains, let's see here, 2, 4, 6 non-bonding electrons. Okay, so neither of these are 0, which is not great. They are close to 0, and we do have a negative formal charge on the more electronegative atom. But remember, nitrogen itself is pretty electronegative too, right? It's right there up next to oxygen. So let's see if we can't do better. Let's see if we can't play around a little bit. So what if we were to take one of our non-bonding pairs on oxygen and create a bonding pair to nitrogen? If we were to do that, we would have something like nitrogen now doubly bound to oxygen, which would have 2 pairs. And then to accommodate that space for that double bond, we would see that these guys pair up. Might have something like this. Let's do a formal charge on our nitrogen. 5 valence electrons when unbonded, minus, now we have 2 bonding pairs, 2 lines connected to nitrogen, plus 3 electrons that are not bonded. Oh, okay, we get a formal charge of 0 on the nitrogen. That is boding well. We like formal charges of 0. Now what about the oxygen? 6 valence electrons when not bonded. This is purely based on the group of oxygen, right? It's in the 6th main group column on the periodic table. And in this particular Lewis dot structure, I now have 2 bonding pairs connected to my oxygen, or 2 lines drawn. And then I also have a total of 4 electrons that are not involved in bonding whatsoever, my non-bonding electrons. So 6 minus 4 plus 2, that's 6 minus 6. Ooh. This is more stable than this guy, which is okayishly stable. So we would say that the Lewis dot structure of nitrogen monoxide would look something like this. And if you were to count up your octets, right, 2, 4, 6, 8 on the oxygen, but in this case with the nitrogen here, we'd have 2, 4, 6, 7. And it's because of that initial odd number of valence electrons on the nitrogen that we have this odd number of valence electrons in our Lewis dot structure surrounding that nitrogen atom. And this is the best we can do. So this is an exception to octet. So the first exception was atoms in a covalent compound that possess fewer than 8 total electrons. And the second is that atoms in compounds that contain odd number of total electrons. So this would be our most stable Lewis dot structure. Okay. The third exception to octet is for compounds containing atoms past n equals 3. So these are atoms with more than 8 electrons. And when I say past n equals 3, I mean like past like the 3p. So we're going to start with our nonmetals of phosphorus and sulfur and heavier. Now the exception that happens here is not that we don't fulfill octet in the sense that like we have less than 8 valence electrons around each atom in our compound. But what happens here when we've got these kind of larger elements is we can exceed or extend octet such that we can have 10 or even 12 valence electrons max. And the reason why we can do this is because by the time we're at n equals 3, especially for elements of like phosphorus, sulfur, and anything that comes after that, anything heavier, is once we're at n equals 3, we have now introduced the d orbital. And even though for some of these compounds the d orbital is not full, like they're not transition metals, that d orbital can still act as kind of like a storage space or a storage unit to accommodate these extra electrons. So when we're at n equals 3, we have d orbitals, which allows for extra space to house any extra electrons. So an example of this would be something like Pi5. So phosphorus, looking at our periodic table, phosphorus has 1, 2, 3, 4, 5 valence electrons. Iodine is a halogen. This has 7 valence electrons. There are 5 of them. So 7 times 5 is 35, plus 5, this is 40 electrons total. And let's continue this on the next page. If I were to then do my symmetric placement of my iodines around my phosphorus, I might have this kind of pentagon shape. And then, according to my Lewis dot structure drawing rules, I would connect each of these iodines to my phosphorus using a single bond. So in doing so, I've used up 2, 4, 6, 8, 10 of my electrons that I'm allowed, leaving me with 30 electrons. And I'm going to now place those around my outermost atoms, starting with the most electronegative. These are all iodines. It doesn't matter which I pick. So I'm going to start filling in octets. So I've used 6, 12, 18, 24, 30. Oh, look, I've ran out of electrons. So I cannot add any more on phosphorus. And if I were to look at the octet on the phosphorus, I would see that yes, all my octets on iodine are fulfilled. That's what I just did. But notice I've got 5 single bonds to phosphorus, 1, 2, 3, 4, 5, each containing 2 electrons. So that is 10 valence electrons on phosphorus, which disobeys octet. So why could that happen? Let's again look at the full electron configuration for phosphorus. Okay, so I am here, n equals 3. So if I were to follow Aufbau, let's go ahead and do my noble gas core. So I would have neon, and then 3s2, 3p123. And in theory, right, what I would fit next was my 4s and then my 3d. Where 0 saying I don't have any of these electrons here. And it's specifically this 3d that acts as my storage unit. This is what allows me to kind of have excess electrons around phosphorus if needed. So this compound does exist. It is stable. This is the most stable Lewis dot structure. And even though it has 10 valence electrons on the phosphorus, it disobeys octet. This is still something that happens. So just be mindful of these exceptions to octet, where you have atoms with odd numbers of electrons, atoms that have a total of more than 8 electrons, so anything past phosphorus or sulfur, and then atoms that have fewer than 8 electrons. These are all things that might break your octet So don't fret if that happens. All right, in our next video, we are going to move away from the Lewis model and instead move into a more quantum mechanical founded model of bonding called valence bond theory. So I'm going to introduce valence bond theory to you, and then we're going to talk about some of the kind of like main ideas and results that come from valence bond theory to wrap up lecture today.